Hello everyone! Thank you for attending the BAS Electrochemical Webinar 2022 Summer. I'm Miho from International Sales Team, and I will be the moderator. Today, it will be the first lecture introduced by Professor Masa-aki Haga from Chuo University. This is a first lecture of a series of lectures in the field of coordination, chemistry, and electrochemistry, introducing basic electrochemical methods and electrochemical applications, with a focus on organic complexes. Today's theme is coordination chemistry and electrochemistry. First, introduction of inorganic electrochemistry.
Hi, I'm Masa-aki Haga. I have been studying inorganic electrochemistry and surface assembling for molecular functional devices. I have been teaching at Chuo University, Tokyo for 25 years and retired 2 years ago, but I'm still continuing my research as an emeritus professor. In this seminar, my title is Coordination Chemistry and Electrochemistry, and I'm talking about the electrochemical methods such as cyclic voltammetry and rotating disc electrodes, so on, particularly focusing on how to use the electrochemical technique and how to analyze the data, particularly for applying inorganic complexes. Today, I'd like to introduce basic concept of electrochemistry and cyclic voltammetry. One of the big global environmental problems in 21st century is to stop the global warming. To tackle this problem, the United Nations adopted the SDGs, Sustainable Development Goal, in 2015. To reducing the carbon dioxide emission, we should reduce our reliance on fossil fuel, such as oil and coal, but turning to renewable energies such as solar, wind, and hydroelectric powers. Creating a global-scale sustainable energy system is an urgent matter. In this figure, possible future sustainable pathway for the production of important fuels and chemicals are shown, including hydrogen and ammonia, by replacing the conventional energy productions. By considering the future energy source, hydrogen-oxygen generation reactions, carbon dioxide reduction, photoenergy conversions, and battery storage become important matters. In particular, in order to catalyze the reactions smoothly, the electrocatalysts play an important role for the development of this field. Here's one example, a model of the oxygen absorbing center in photosynthetic system 2. The detailed X-ray structures of the oxygen absorbing center in nature was reported recently, in which are cluster structures composed of manganese and calcium, as shown in these figures. To mimic the water oxidation reaction in nature, many studies has been reported. Recently, pentanuclear ion complex consisting of 5 iron ions linked by nitrogen containing bridge ligand has been synthesized, and the redox behavior was clarified by cyclophotometry. As shown here, 5 reversible redox waves correspond to ion 2 to 3 were observed in the Bortanogram. When water was added to the complex, the oxidation catalytic waves with the large rise of the current around 1 volt was observed, indicating that these ion clusters act as the oxidation catalyst for efficient water oxidation to dioxins. Thus, it is possible to evaluate catalytic activity by using electrochemical methods such as cyclophotometry. Here is a small list of the molecular structures of metal complexes which has been used as an electrocatalyst. In energy conversion, namely HER stands for hydrogen avoiding reactions, OER stands for oxygen avoiding reactions, ORR stands for oxygen reduction reactions, and carbon dioxide reactions. These complexes act as the electrocatalyst as shown below, particularly for below reactions, and their electrocatalytic mechanism have been elucidated using electrochemical techniques such as cyclophotometry and rotating disk electrode photometry. The clarification of the catalytic reaction mechanism have greatly contributed to facilitating the development of new catalysts. Metal complexes are composed of metal ions and ligand, both of which are bonded by coordination bond. By selecting ligand, we can design metal complexes with help of computational chemistry and develop new structures and functions for molecular electrocatalysts and molecular devices. Electrochemistry is a useful technique to evaluate functions of complex such as redox potentials and spectral change, and also the homo-lumo level, and act as a mediator as a catalyst. Here is a brief outline of what I'm going to talk about, futures and its titles. Today, I will present short introductions of inorganic electrochemistry by showing the example of. Then I will discuss the concept of electrode potentials and relationship between mass transport to the electrode and current, and the current voltage curve obtained from cyclophotometry. The second part of the lecture will discuss the basics of cyclophotometry, which is the measurement of the current voltage curves, which is called Bortanograms. Next time, the analysis of cyclophotogram will be discussed from the viewpoint of electrode reaction mechanism. Furthermore, I will touch on the combination of CV and spectroscopic method to characterize the redox species. First, let's consider the equilibrium between the electrode and solution species. When a platinum electrode is inserted into the solution, analyte, in this case, ferrocyanide and ferricyanide, electron transfer takes place till some dynamic equilibrium is established. with the platinum electrode. The equilibrium of the electrochemical potential between the analyte and the electrode is described by the Nernst equation shown here. In other words, the ratio of oxidized and reduced form activities of ion in the solution determine the potentials. However, we cannot determine the absolute potential values in a single electrode system. Electrochemical potential cannot be defined between two different phases, such as solid electrode and analyte in solution. To overcome this difficulty in a single electrode, the potential difference between two electrodes can be measured by wiring two electrodes. So, it is possible to determine the relative potential difference between two electrodes in which one side acts as a reference electrode. The reference electrode should be ideal non-polarizable electrode. In this case, silver chloride electrode show a well-known stable reversible redox couples, therefore used as the reference electrode. Two types of electrodes are present. One is polarizable electrode, in which any charge does not pass across the solution metal interface by changing the potentials. One example is mercury electrode in potassium chloride solution. However, in generally, real electrode behaves the ideal polarizable electrode within the specific potential range and behave as capacitors. On the other hand, when the current flow in the cell, the potential does not change and fixed. This electrode is called as ideal non-polarizable electrode. Silver chloride electrode is a typical example of non-polarizable electrode. Therefore, the stable potential system with non-polarizable electrode commonly used as the reference electrode, and their electrode reactions are shown here. The first electrode is a normal hydrogen electrode, abbreviated NHE, and this potential was defined as the standard electrochemical reduction potentials by IUPAC as 0.40 volt. The second example is silver chloride electrode, which shows the plus 0.22 volt at 1 molar chloride concentrations. The third example is caramel electrode composed of mercury chloride and mercury, which is shown 0.268 volt. These three electrode systems are used primarily in aqueous solutions, aqueous systems. When the solvent is a non-aqueous solvent, such as dichromycin or acetonitrile, the electrode reaction system with ferrocin and ferrocenium ion is often used as an internal reference. Standard house cell electrode potential for various electrode reactions have been reported and list precious hydrogen electrode. These standard redox potentials are very useful databases that provide the basics for constructing electrochemical systems in various situations, such as thermodynamically determine whether the redox reaction occurred, or selecting the candidate electrode materials for battery applications. When the electrodes are in electrochemical equilibrium, the electron transfer on the electrode occurs at the same rate in both left and right directions, maintaining the equilibrium. The Nernst equation then holds. According to the chemical thermodynamics, the standard Gibbs free energy change is defined by this equation using the standard potential E0 in the half cell reactions. In other words, the thermodynamics gives energies which indicate the direction of the electron transfer reactions is related to the electrochemical potentials. This indicates the standard electrochemical potentials provide a measure of direction of electron transfer reactions. In these days, many analytical methods are available, and each method provides us useful chemical information about the chemical compound. For example, ruthenium twisted pyridines in the NMR provide us chemical shift and Smith-Spin coupling were obtained, and the information of the chemical environment between ligand in a complex are determined. And for UV spectroscopy, give us the absorption band, and from which the energy level through electronic transition can be determined. Similarly, cyclic protogram we will refer to as CV from now on can be described as electrochemical spectroscopy, as same as the other spectroscopic method. CV gives redox potentials and kinetics of electron transfer. By analyzing the measurement protograms, one can obtain the information on the homolumo level from redox potentials and redox reactions of the complex. For CV measurement, 3 electrode cell is generally used. First, working electrode is the electrode where the redox reaction takes place. The working electrode is composed of inert materials such as platinum, glassy, carbon, and gold. Next, counter electrode used for the complete circuit between working electrode and counter electrode. The counter electrode is also composed of inert materials such as platinum wire or seed. Finally, reference electrode is a non-polarizable electrode which point are stable, well-known potentials. Thus, the applied potential is reported versus the reference electrode. The cell contains the analyte solution with the addition of supporting electrolyte, which minimizes the solution resistance. Also, the cell was degassed by inert gas flow to remove redox active dioxygen in solution. To run the electrochemical experiment in 3 electrode cell, the current flows between working electrode and counter electrode. The polarization on the working electrode is controlled by applying potential versus reference electrode. In cyclic potentiometry, the triangular shaped waves or the potential sweep is applied to the working electrode, and the electron transfer due to the redox reaction at the electrode is detected as the current. During the CV measurement, the solution is kept in a standstill condition without stirring. typical protogram is shown here. These protograms contain a lot of information, which will be discussed later. Electrode reaction is a heterogeneous system, therefore mass transport to the electrode play an important role. Mass transport determines the current values in which the analyte in solution moving in the vicinity of the electrode, so that electron exchange takes place between analyte and the electrode. Mass transport of the analyte to the electrode include three modes: diffusions, migrations, and convections. Diffusion takes place by concentration gradient. Migration takes place by electronic potential gradient, and convection occurred by mechanical motions such as stirring or rotating the electrode, and also the gravity operating on the density gradient. In cyclic voltammetry, the diffusion is the only significant transport process to contribute the current. In order to keep these conditions, the supporting electrode is added to the solution 10 times excess than the concentration of the analyte to reduce the migration effect. Also, by suppressing the effect of the convections, the solution does not stir or agitate. The flux J0, which is directly proportional to the current, will be proportional to the derivatives of the concentration gradient. Therefore, the current will then represent the reaction rate from this equation shown here. Before describing the concentration change upon linear sweep protogram, or CV, let us consider the temporal concentration change by the potential step on the electrode surface. This figure shows concentration profile upon the potential step. X-axis shows the distance from the electrode, and Y-axis is the relative concentration of the analyte. At the beginning, the concentration on the electrode surface is the same as the bulk concentration at the zero time. But after 0.001 second of the potential step, electrolysis occurred on the electrode surface, then the concentration gradient is generated at the electrode surface. The crossing point of the separating line for this potential gradient is called the thickness of diffusion layer. When the time becomes longer, this diffusion layer expands, which leading to the slope of the potential gradient becomes smaller. Since the current is proportional to the gradient, the observed current value becomes decreased with time passed. This time dependent on the current is given by these equations known as the Cottrell equation. Now in CV, the triangular shaped waves is applied to the electrode. The electron transfer response at the electrode solution interface is detected by current response. As a result, a CV is obtained by plotting the applied potentials on the horizontal axis and the current response obtained from the electron transfer at the electrode on the vertical axis. In other words, the ET response is converted and plotted as the EI response. When the potential is forward scanned to the positive directions, and at the switching potential, the scan is reversed. By accompanying this potential scan, the anodic peak, which the electron removed from the anolyte, is observed at the forward scan. And for the reverse scan, the cathodic peak is observed at the anodic peak potential where the sample is oxidized. On the other hand, the cathodic peak potentials where the sample is reduced. Now, in CV, when the linear sweep potentials is applied, the concentration distance profile of the analyte is changed with time progress. As you can see, the thickness of the diffusion layer expands with the time. Since the concentration gradient expressed as the current values, gradient reached a maximum value at this time, and therefore the slope becomes smaller, indicating degrees of the current. In other words, the CV will give the peak of the current at the EI curves. This potential current EI curves having peak is characteristic of cyclic bertagrams. This peak-shaped IV curves on CV derived from the diffusion limit mass transfer. Here is the concentration distance profile on CV. At each point on the CV curves from A through G, the concentration distance profile from the electrode are shown here. Each graph indicates the oxidant and reductant concentrations from the electrode distance as the different colors lined. The important point in this concentration distance profile is that at point E to G, invergence of concentration distance profile took place. This nonlinear concentration distance profile remained after the potential scan finished. This comes from the diffusion layer expansion and slow mass transport of starting analyte. To illustrate the cyclic bertagram as a graph, there are two conventions for graphical depiction to show an EI plot. The first, which has long been used in the United States, is to plot the right side of the x-axis as the negative potentials, the left side as the positive potentials, and the upper side of the y-axis as the cathodic current, and lower side as the anodic current. On the other hand, IUPAC recommended that the display with the right side of the x-axis as the positive potentials and the left side as the negative potentials, and the y-axis with anodic current are positive. In both cases, it is decided that the EI curve associated with the triangular wave scanning is to write the protogram in a clockwise directions. Sometimes people draw the wrong CV diagrams in paper in counterclockwise direction. So you have to be careful and do not make a mistake when you read journal papers, even for textbooks. When potential is applied to the electrode at the interface between electrode and electrolyte solution, through charge transfer process are observed as electric current. First, when the positive potential is applied to the electrode, negative ions in the solution are attached to the electrode surface, forming an electrode double layers at the interface. The charging current of this electric double layers also appeared whenever the potential is swept in a cyclic botograms. This charging current is proportional to the first order of the sweep rate. On the other hand, the process of electron transfer from the bulk solution to the electrode surface by diffusion, which is called Faraday current. In this case, the current is proportional to the square root of the sweep rate. In CV, the total current is a combination of the non-Faraday current due to the charging by the moving of the ions in the double current due to the electron transfer through the interface. As mentioned before in CV, the thickness of diffused layers from the electrode is expanding with time towards the bulk under the potential scaling. The bottogram is a peak because the mass transport of this substrate substance does not move fast enough by time upon the potential shift. As a result, the peak shapes appeared. On the other hand, if the mass transport of the substance to the electrode is forced by rotating electrode, the thickness of the diffusion layers becoming constant under the potential shift. The limiting current value obtained, even the higher potential values, the diffused layer is constant. Therefore, S-shaped current voltage curve is obtained. This is called steady-state botograms. These two botograms shows a sharp contrast on the wave shapes arising from the difference of time-dependent diffusion layer thickness. Photometry can be classified in two main methods. One is the steady-state method, and the other is transient or non-steady-state method. In the steady-state method, the diffused layers on the electrode remain constant with respect to the potential sweep. The steady-state method includes the rotating disk method using forced convections and microelectrode method. In transient or non-steady-state method, there are three types of method. The potential control method includes the lump wave is applied, the potential step method, in which potential step or pulse is applied, and pulse photometry method. I will discuss cycle botograms and rotating disk photometry in the future. To summarize today's important point, the electrochemical method is not homogeneous reaction systems. The electron transfer at the interface between the electrode and the electrolyte solution took place. In that case, the mass transport of the analyte to the electrode dominate the reactions. The current represent the electron transfer reaction rate on the electrode. The current responds to the flow of the electrons. The diffusion of the material determines the value of the CV current. It is not possible to control both current and voltage at the same time. Therefore, two methods can be used. One is potentiostatic method, and the other is galvanostatic method. There is a list of the reference books and review papers. I will stop my first seminar at this point. If you have any questions and comment, I'll be happy to answer.
Thank you, Professor Haga. I wish you enjoyed the lecture. If you have any question regarding to the lecture or other topics, you can contact us. The email is here. In addition, the movie of a variety of topics you can watch here in the BAS channel, which you can follow and have access to the latest news, including the past webinars. The next webinar we are working out to have for October. It will be the second lecture in the field of coordination chemistry and electrochemistry. For today, thank you again and have a nice week.